Richard Feynman, known for his engaging and insightful lectures, could bring the concept of planetary motion around the sun to life using fundamental principles of physics. Integrating frequency wave theory into such a lecture might have provided a unique perspective on the dynamics of celestial mechanics. In classical mechanics, as taught by Feynman, the motion of planets around the sun can be compared to harmonic oscillators if simplified to two-body systems. Frequency wave theory can enrich this analogy by considering the orbits of planets as waveforms that repeat over each orbital period. These waveforms can be thought of as sinusoidal waves where the frequency is related to the orbital period, and the amplitude could be analogized to the orbital eccentricity. Feynman could use frequency wave theory to explain the concept of orbital resonance, where two orbiting bodies exert a regular periodic gravitational influence on each other, typically because their orbital periods, or frequencies, are related by a ratio of small integers. This is similar to how two oscillating systems might come into resonance, amplifying the amplitude of motion. While not directly observable with planets of our solar system due to their relatively weak gravitational effects, Feynman might have speculated about how the motion of larger masses, like those of binary stars or black holes, could produce detectable gravitational waves. In frequency wave theory, these waves would be ripples in spacetime created by the motion of mass, analogous to how moving charges generate electromagnetic waves in classical electrodynamics. Bridging his expertise in quantum mechanics with celestial mechanics, Feynman could discuss the wave-like behaviors of particles at quantum scales and ponder whether any quantum mechanical principles, such as wave-particle duality, could metaphorically apply to macroscopic bodies like planets, treating their paths as probabilistic wave functions rather than deterministic orbits. Using Fourier analysis, a method well loved by Feynman that breaks down waveforms into constituent sine and cosine waves, he could explain how complex orbital interactions such as those seen in multi-body systems like the asteroid belt or Kuiper belt might be analyzed to reveal underlying patterns and frequencies that govern their stability and evolution. Integrating frequency wave theory into a lecture on planetary motion could provide students with a richer understanding of how celestial bodies interact through both gravitational forces and resonant phenomena. It connects the intuitive visualizations of orbits as waveforms with the mathematical rigor of physics, showing the elegance and interconnectedness of the universe in terms Feynman famously celebrated.